Hi everyone, my name is Laura Zhang, and I'm going to be talking about traffic-aware autonomous driving with differentiable traffic simulation. Here are my collaborators Sunghyun Son and Ming Lin, and we are all from the University of Maryland, College Park. So to start, I want to give a summary of contributions. Firstly, we create a driving dataset with traffic simulation annotations. Second, we use gradients of traffic flow to improve sample efficiency in mixed autonomy tasks. And lastly, we propose a method for traffic-aware autonomous driving. So to motivate why we do all of this, we need to talk about mixed autonomy. Mixed autonomy describes a traffic system containing both autonomous vehicles and human-driven vehicles. And while we don't observe this now in the real world, it is an unavoidable multi-agent problem that we need to think about as autonomous vehicles become more ubiquitous. So the mixed autonomy task can be visualized here, where a vehicle agent interacts with traffic via acceleration actions to improve global objectives like average velocity, energy consumption, comfort, etc. The core idea is that autonomous vehicles can learn to positively influence the traffic around it. So we seek to answer the question, how do we apply learning from mixed autonomy problems to autonomous driving policies? So given driving sensor data and its paired local traffic state, can we improve global objectives for all vehicles in the traffic system? So now let's get into the method. We do this in two phases, where phase 1 is for intentionally learning acceleration via an acceleration agent, which is in red. So this agent learns via on-policy reinforcement learning methods in the ICRA driving simulator environment, and it's rewarded based on global objectives. So we also note that the expert agent in ICRA provides optimal steering control in this step. So again, to emphasize, all it's learning is how to accelerate. Then in phase 2, the acceleration agent directly supervises the acceleration controls of a driving policy, while the rest of the controls, such as steering, is supervised by an offline dataset. Notice that the method for driving policy learning is easily interchangeable with other methods, as long as acceleration can be separately supervised by the phase 1 acceleration agent. So to repeat it again, in this step, we learn everything else, and this phase of the model is directly supervised by phase 1 for acceleration. So in addition, we also improve sample efficiency in phase 1 with traffic gradients. Now you might wonder, what is a traffic gradient? So we can just think about it as they change from one state to the next in a traffic simulation. If we know exactly how vehicles move in the current time step with respect to the last state, then we also know how changing the action can also change the resulting environment, and then how the resulting environment can change the resulting reward. So the key idea is that now we can pick some augmented action which has a slightly higher reward since we know exactly how action relates to the reward via the differentiable environment. So here are some results on how sample efficiency improves learning outcomes for phase 1, where TRPO is our baseline on policy algorithm and diff TRPO is the sample enhanced version. Here we visualize the last results qualitatively on a figure 8 traffic simulation network. And we notice that our method on the right has an overall higher average velocity for all vehicles in the system, whereas the baseline on the left gets stuck in the upper right corner and the vehicles come close to a stop. And here we do a comparison between average velocity and fuel consumption across 26 ICRA test scenarios. Across most scenarios, our method in blue consistently improves traffic flow around the autonomous vehicle while still maintaining about the same fuel consumption, even though there is a direct relationship between increasing acceleration and increasing fuel consumption. Here's a qualitative visualization of scenario 1 from the ICRA benchmark scenarios. We show this example as a failure case of the baseline model on the top due to learning a poor acceleration policy. And notice how the vehicle is unable to accelerate despite the traffic light being green. And on the top right, we show the average velocity of the entire lane around the ego vehicle across time steps. So to wrap up, we have some key takeaways. First, our phase 1 model supervises phase 2 in a distillation-like fashion with respect to acceleration control. Secondly, results in our paper reflect not only improved societal objectives like traffic flow and fuel consumption, but also individual objectives on quality of driving. And lastly, our method complements existing work in autonomous driving. Our method can be implemented as a wrapper on top of existing methods thanks to traffic co-simulation. Also, we want to mention a couple limitations. Current traffic simulators are non-parallelized and unoptimized for learning tasks, so phase 1 can take a long time to train. Also, existing benchmarks in autonomous driving do not consider difficult traffic flow tasks and thus might undermine the effects of our method in terms of improved global objectives. And that is all. Thank you for your time, and if you would like to learn more about our project or read our paper, please visit our project website.